Good afternoon, everyone. My name is Dick Peltier, and it's my pleasure to welcome this afternoon's colloquium speaker back to the Department of Physics of the University of Toronto. Caulfield is visiting us from Cambridge University, where he is head of the Department of Applied Math and Theoretical Physics. Colm finished his doctoral degree at Cambridge in the same department in 1992, after which he joined us here in my group for 3 years as a postdoctoral fellow. During that time, he made many visits back and forth to Japan, but after finishing his postdoctoral fellowship, he took up a junior faculty position at the University of Bristol in applied mathematics, stayed there for several years, and then moved to the University of California in San Diego, where he also spent about 4 years, returning afterwards to Cambridge University, to a position which was joint between what was then the BP Institute and DAMTP. This afternoon, he's going to speak to us on the topic of mixing up the climate. And it's a story of how the mystery of stratified turbulence will determine much of what our future has in store. So please help me in welcoming Caulfield to this colloquium.
Thank you very much, Dick, for that very kind introduction. And he's quite right, it is a great pleasure to be back here again. It is just under 30 years when I first arrived here as a fresh-faced postdoc to come and work here at this department. And it was a really wonderful 3 years that we spent here. And I'd like to take the opportunity again to thank the department for the kind invitation for me to come here, and how nice it is to actually be able to revisit Toronto, even in the rain of today. So in the next 50 minutes or so, I will try and tell you about this problem, and I'll effectively be trying to explain what these two pictures are here that are examples of recent work in my group, where we have been trying to use data-driven methods to understand stratified turbulence. So effectively, this talk divides into 3 parts. There's first trying to tell you why stratified turbulence is important and why we should really be concerned about it, what its potential effects on the global climate are, and then present the challenges and some starting work we've done towards it to address those challenges, just in terms of reanalyzing observational data and reanalyzing numerical data using data-driven techniques. Of course, I should mention my sponsors, the Engineering and Physical Sciences Research Council and the Natural Environment Research Council, parts of UK research and innovation. So why are we interested in stratified mixing? Well, of course, there's this beautiful dynamical system that we all know and love, the world's oceans. This is an amazing data set. It's quite old now, from Kathleen Doan, of ocean surface currents from altimetry in real time. And really, this is just a classic fluid dynamical pretty picture to show you of the great complexity of the different currents that are going on in the world's ocean. The Gulf Stream that ensures that Ireland and Britain are not the frozen north. You can see the clear effect of the equator by these strong currents along the equator. The strong effect of the Antarctic circumpolar current by turning back. You see the Agulhas retroflexion that's going on there. And you see that there's just this rich combination of different currents that are going on in the world's oceans. And why they're relevant to, why I particularly want to say they're relevant to the climate emergency, is that the ocean is rapidly being heated up. Here is, it's quite old now, nearly 3 years old, from the newspaper that I read every morning, not just the football pages. And you'll see that there is this clear evidence that the ocean is just getting warmer and warmer as we are adding more carbon dioxide and methane to the world's atmosphere, and also, of course, affecting ecosystems and such like. And so we really have to be concerned about how heat is being transported in the ocean because of the influence it has on our global climate system. And it's also very important to appreciate that the amount of heat that's transported in the world's ocean is really quite enormous. It's measurable at the order of petawatts, of the 10 to the 15 watts of the poleward transport of heat in the various oceans, the Pacific, the Atlantic, and the Indian Ocean and such like. And that transport of heat is crucially important for determining the global climate system, not least because of this quite amazing little stat. Of course, we're all become aware now of the, because of billionaires wanting to go to space, and the definition of where the space starts is at about 100 kilometers, or at least that's Jeff Bezos's definition. It's what's called the Kármán line. It's where you stop actually having aeronautics. Planes are not experiencing any lift, but they're effectively orbiting. So you have the astronautics. And if you think of a column of air starting with some cross-sectional area, and the whole column of air up to the edge of the atmosphere, this 100 kilometers, then you ask yourself, for that volume of gas, how much heat do I need to pump into that volume of gas to increase the temperature by 1 degree? That's a certain amount of heat. And then the amount of heat that you then need to increase the temperature of the water in the ocean by the same, by a 1 degree, you need a volume that only extends down 3.4 meters. Now, if you remember that the ocean is typically 4 kilometers, 5 kilometers deep, that is just to give you a scale of the idea that the heat content of the ocean and the modification of the heat content of the ocean is crucially important and vastly greater than that is involved in the atmosphere. Now, at the moment, while we still have ice on Greenland and ice on Antarctic, a key component of the ocean circulation is that cold, deep water is formed in the polar regions. It goes down to the bottom, and the incoming thermal radiation, very, very simplified, is heating up the upper mixed layer. But there has to be something else that's going on, this concept of mixing, to make sure that we don't just have a hot reservoir of hot water at the top and a reservoir of cold water at the bottom. We've got to have some mixing process that's going on, and understanding what that mixing process is crucial to modeling the world's climate system going forward. Now, if we think about how we produce models for this, and we want to understand how the climate system is changing as we're rapidly perturbing it, we have to really think about possible areas of uncertainty. And if you think about the models, that I've heard some very interesting talk to people here, the 1/48th degree simulations and so on, you're getting down to maybe a kilometer scale, maybe slightly less now in your climate models, but you can have processes that are happening on scales much smaller than that are crucially important. And so if you think about just one issue of interest to people, at least in the Netherlands, it's about how the sea level may change as we go forward over the next 50 to 100 years. What will change that? Well, you'll have melting of ice on land. That will increase the depth of the sea level rise. And also the other component is, of course, as the water heats up, it will expand. And so you want to understand how much heat goes into the ocean and how much water stays in the ocean, either running off land and in terms of the global water cycle. And if you stop and think about what the main regions of uncertainty, well, clouds are a great region of uncertainty. How does the evaporation happen in the tropics? What is the balance between the reflection back of heat because of the albedo effect and then the blanketing effect of the clouds? That's an area of uncertainty. But as I like to say, it's multi-phase flow, it's complicated, it's got thermodynamics. I never liked thermodynamics. Let's not think about that too much. Ice sheets, similarly, very, very important to understand their dynamics. But once again, the key processes there involve phase changes, complex rheology in the ice, very complicated models there. It's an open area of uncertainty. And yet also, in a sense, both of these we can see happening. We can see where the clouds are happening. We can see the ice sheets. But what I want to say to you, effectively, the invisible issue that is very, very uncertain is the mixing that's going on in the interior of the ocean, which is causing this vertical structure in the stratification. It's an area of great uncertainty, understanding not the sort of waves that we see over here, these sort of surface waves, but the waves that are happening in the interior of the ocean because the ocean is stratified. And so just a little primer, of course, of what do I mean? The ocean is stratified. You have vertical variations in density. So if you perturb a parcel of fluid, this is supposed to be, the schematic. Dark blue is is lower and denser, think Oxford. Light blue is brighter and less dense, think Cambridge. If you lift dark blue upwards, it is dense in its environment and it realizes I shouldn't be here. I should fall down to my proper place. It falls to its proper place. It still has velocity there. It therefore overshoots and you can get simple harmonic motion going at this classical frequency, the buoyancy frequency, which knows about the gradient in the density within the system. But if I then think about that sense, so does that mean that all the ocean just bobs up and down at one frequency? Of course it doesn't. Because if I think about forcing the fluid at a frequency lower than this, and so this is a picture due to Barry Ruddick, what you actually are seeing here is a vertical bar. That vertical bar is actually holding a horizontal cylinder, and that horizontal cylinder is then moved backwards and forwards in the fluid at a frequency lower than this buoyancy frequency. And as that happens, you get these beautiful waves going at a characteristic angle given by the ratio of the frequencies. And you see the phase fronts up here are moving downwards, even though the energy is going outwards away from this forcing location. And so what I really want to say is if you have any forcing, any perturbation in a stratified fluid, you get waves. And so the way to think of the ocean and inside is this incredibly noisy place with lots and lots of waves bouncing around with a whole range of different processes. And indeed, many of the people here are studying different aspects of those processes. You can have fronts of fluids of different density. As those fronts propagate along, they will perturb this upper mixed layer. They can cause waves. If you have storms at the top of in the atmosphere, that will once again perturb the mixed layer. You can have waves propagate off that. You have currents going over topography. You can have lee waves or you could have hydraulic control. They will emit waves. Internally in the tide, there are tides moving interior of the ocean, moving backwards and forwards over topography. They introduce waves. And what you want to understand is how these waves break in a very loose sense, because the waves are able to transport momentum all over the ocean. And only when they break and they induce turbulence do they mix and therefore cause this variation in the stratification. And so there's a huge amount of different important processes going on in this picture. And really, I want to say, not in any way that we can address this problem. It's just, let me draw your attention to two particular things that as a mathematician that I'm interested in looking at. Firstly, when you're can we reanalyze observational data of wave breaking near topography, near shore, to understand how those processes work? And then also revisit the large numerical simulations we're able to look at, where wave-wave interactions are leading to turbulence, and can we reanalyze that turbulence, those very, very large numerical simulations, to try and understand how waves break when they interact with each other. And really, this is driven by moving on from one incredibly influential paper due to the great Walter Munk from 1966, who, as a back of the envelope, an amazing back of the envelope calculation, said the vertical distributions in the interior Pacific are not inconsistent with a simple model involving a constant upward vertical velocity of about 1 centimeter a day and an eddy diffusivity of heat of the order of 1 centimeter squared per second, which really is saying that the eddy diffusivity, the transport of heat, the diffusion rate of heat modeling the turbulent motions increases that transport of heat by a factor of 1,000. That's the back of the envelope thing you want to think about. And really, that is the eddy diffusivity can be written in this way. It's the ratio between the complicated thing of if I lift dense parcels up, I will be increasing the potential energy and in principle mixing, compared to that, which is very hard to measure, because how am I going to measure vertical velocity and density fluctuation simultaneously, divided by the thing I have a hope of measuring, which is the density gradient. If I drop a probe through, I may be able to measure that. And so that's really the challenge that was thrown. To try and balance the picture, it seems that this quantity is increased by 1,000, and so turbulence is increasing the transport by something of the order of 1,000. Can we do better? Can we get a better handle on that? Because the final sentence of this abstract says, such internal modes, i.e. the gravity waves type things I'm talking about, can produce shear instability in the Richardson sense. It is found that internal tides, with these waves being formed, provide a marginal but not impossible mechanism for turbulent diffusion in the interior oceans. So kind of inspired by this challenge, we want to see if this is true, can we understand that? And can we extend slightly beyond, supposing it's constant everywhere, but get a better insight into it? And so really, I like to talk about this concept. What does it mean to mix? I like to refer to it as the taxation rate of turbulence by stratification. So if you have a certain amount of energy that's being put into your system through some forcing mechanism or through turbulent production, and you work out the turbulent kinetic energy, you can see you have a transport term, you have as I say, the turbulence production extracting energy from the shear, you might have some forcing, and then this density flux, which is often called the buoyancy flux inaccurately, this buoyancy flux is there as well as viscous dissipation. And if I had no stratification, there would only be viscous dissipation. But as soon as I introduce stratification, so I've had turbulent flow like this with a density stratification like that, the turbulence may mix the fluid up and it could lead you to this fully well-mixed layer in the middle. And if you look at that fully well-mixed layer, that has clearly increased the potential energy of the system. So therefore, this taxation is doing mixing and is eventually converting kinetic energy into potential energy. And so the question is, can we understand how that balance might work? Now, part of the problem is, as I said, we want to have this kind of balance. We say if we say the flow is in some kind of balance, the kinetic energy isn't changing. This is just transport around the system. We won't have any forcing if it's in balance. We have a balance between the production, the injecting energy, and the viscous dissipation, losing it to viscous dissipation, and then this density flux increasing the potential energy of the system associated with mixing. But this is also slightly mathematically unsatisfactory because this quantity saying I lift a dense parcel up, that means I have a vertical velocity fluctuation and a vertical density fluctuation. That is not necessarily mixing, because if I lift a dense parcel up, which is often happening with these waves, if I put that dense parcel down again, I can have reversible exchanges. So it's really not so appealing to think about that. You really want to be able to look at the irreversible exchanges. And so one nice way that I've started to want to think about that is to get away from the energetic interpretation of mixing, but just look at it as a homogenization process. It's a process by which a density distribution which has variability and so variance compared to a mean profile, a background profile. How do I reduce that variance to homogenize the fluid? So I look at a quantity which, if the background gradient of density that I'm comparing it to is constant, can be considered to be the available potential energy, but it can be generalized away from it. Second order fluctuations of density, and write down an equation for that. Well, I'll see that this quantity will increase because of this density flux term, but will decrease because of this chi term, which I'm defining this way, and it's the destruction of buoyancy variance. And what's really nice about this is it's clearly sign definite. It's just it's the magnitude of the gradient of the density fluctuation squared, appropriately scaled, and it clearly involves the diffusion, right? It has the diffusivity of whatever's causing the density involved in it. And so it's kind of more natural, I would argue, to look at this quantity chi rather than the buoyancy flux. And particularly if everything is balanced, they're equivalent. And so really the challenge put to us by Monk to understand kappa T is really understanding how chi varies compared to n squared, the background buoyancy frequency. And so this taxation rate, which could be called as flux coefficient, is just the ratio of chi compared to epsilon. The rate at which I'm dissipating density fluctuations compared to the rate at which I'm dissipating velocity fluctuations, which is kind of very, very appealing conceptually as what I want to do. Okay, but wanting to model things, the natural question is, okay, can I come up with appropriate ways to parameterize this quantity in terms of background quantities? And one natural way to do it, which is shown from these, like this beautiful, well, I think it's beautiful, this sheared breaking wave, this turbulence in a forced large-scale turbulence in a stratified fluid, or this classic shear instability, this Kelvin-Helmholtz instability, they've got this idea that you somehow or other, an overturning is happening within the system. Somehow or other, you're extracting energy from shear and you're causing it to mix up the fluid. And indeed, observational data from Matthew Alford shows that there is a very good correlation between small value, situation where you're expecting to have shear instability, i.e. where this parameter, this Richardson number is small, and regions where you see high values of dissipation, which are likely to be related to turbulence. And this Richardson number is a natural parameter of the background flow. It's the ratio of the time scale associated with stratification. So if the stratification is very strong, you lift a dense parcel up, it wants to go down very quickly. And then the shear, which is the time scale associated with the kinetic energy in the system, if that's very large, I'm being able to really get a lot of turbulence production and kick the system very hard. And so it seems natural that small values of that will be associated with these sort of nice overturnings. But the problem that you might have with that is that that is just one of very many parameters that are within the system. And so you can't see it, which is perhaps better with the chat obscuring it, because what I've got written here is properties and religions. Because there's effectively religious debates in the literature and the conferences about which parameters could be important or not important to model this particular process. So it could be, because what would be the property of parameters we've got? We've got properties of the fluid, like the viscosity or the thermal diffusivity of the stratification. I've already mentioned we've got properties of the background, the buoyancy frequency and the shear. But then if you actually think about a real system, what does the overline mean? What is the form of averaging I'm doing? How is it, what is the spatial, is it spatio-temporally varying? Because of course we might have a different shear near the boundary than in the interior of the ocean. There are properties of the turbulence, of course, how intense the turbulence is, its magnitude of the kinetic energy, how intense its dissipation rate is. But you can think of those intellectually or philosophically, I would say, as properties of the fluctuation field of the velocity. And you can equivalently think of properties of the fluctuation field of the density. This quantity, which, as I say, in many circumstances can be thought of as available potential energy. This quantity chi, the dissipation rate of the buoyancy variance. And so I can write these in, I can imagine, depending on what my religious views are, I can say which ones of these parameters are likely to be important to parameterize the key quantities in mixing. Now, indeed, a very strong dominant model is to say the taxation rate is a flat rate, that basically the density flux and the dissipation rate are linearly related. And I will say that something now, that is having a stronger statement. Not only are they linearly related, but they are being sampled from the same probability distribution function. And that is something that I'm going to sort of show is just not right. But if you suppose they're linearly related, so the more dissipation you have, the amount of mixing goes up in lockstep, and you say the taxation rate is some fixed value, this 20%, then the thing you're interested in, the diffusivity, can be related to this gamma, the viscosity of the fluid, and this non-dimensional group here, which is commonly called the buoyancy Reynolds number, which is a hybrid, basically, of properties of the turbulence, properties of the background, and properties of the fluids. It's a bit of a mess. And it's often clouded. People talk about this quantity, and I'm certainly somebody who has made sins in this way, to look at gamma and say high gamma is important. But what you're actually interested in is the amount of diffusivity. And so only high gamma is important when this quantity buoyancy Reynolds number that's pre-multiplying it is important. And then, but the real devil is, there's absolutely no reason that gamma itself is not itself a function of the buoyancy Reynolds number, or is not a property of the turbulence, this turbulent fluid number, or it could be a property of the Richardson number, or it could be a property of the fluid, the Prandtl number. We really don't know. This is the quantity we want, and we have got no further on because it could depend on all these different parameters. And indeed, a more appealing way is to say the thing we actually want to model is chi, because as I said, that's a more natural way to think what the eddy diffusivity is. It's chi relative to n squared. So I've tried to set the scene now for saying why we're interested in this and then trying to distill to you some of the actual physics of the quantities that we're interested in. But if you look at the literature, and particularly you look at review articles, they're all over the place. In 2008, Greg Ivey, who's actually at the University of Western Australia, but then colleagues at Stanford, which is effectively the Stanford School, are saying laboratory and numerical work indicate that either when the buoyancy Reynolds number is small or when it's large, the mixing efficiency, the Flux-Richardson number, which is relatable to this gamma quantity, tends to 0. And the use of saying it's about 0.2 in field situations in these limits cannot be justified. Right? So that was the story about just over 10 years ago, 13 years ago. And then 3 years ago, the school at Washington, Mike Gregg et al., said, okay, it has long been understood that mixing efficiency is unlikely to be constant, but kappa from traces and microstructure evaluated with gamma being 0.2 agree better than do coefficients and efficiencies from simulations and experiments. So that's a beautiful sentence in the paper. We know it's not constant, but when we assume it's constant, it fits the data better than not assuming it's constant. So just turn that around in your head for a minute. It's like, whatever, 0.2 works, right? So then the question is, you know, can we try and understand that? And then I said, although there has been a large range of deeply insightful research contributions, to be polite, it still remains extremely difficult to say anything generic about mixing. Basically, we have no idea what's going on. And so I suggested as a future issue, which is what I'm now going to talk about in the next 25 minutes, the situation is unbelievably important, unbelievably complicated. There's a whole slew of different physics-based models we can present, and none of them really particularly fit with the data, and we can't explain. I'm then saying we have a heck of a lot of data from observation and from numerical simulation. Why don't we try and reanalyze the way we do it? Why don't we use data-driven techniques to reanalyze the old data, or the data we have, and see if we can get alternative insights? So that's now what I'm going to talk about now. I'm going to talk about 2 different examples where we've tried to do this. Kind of not saying I've got the answer, but I'm going to tell you about 2 different situations where we appear to be getting some new insight by using data-driven methods. And the first is a reanalysis of some observational data from Palau, a rather nice place. There's Australia, a rather nice place in the South Pacific to do observations, this beautiful island. And they did the sequence of observations of a reef in Palau and took 300 profiles of microstructure. So they take this, they drop this thing over the side of the boat, let it go down 300 meters, and measure different quantities within the flow. And so I've mentioned already this dissipation rate. This is the profile of dissipation rate. This is a profile of chi. There's an incredible amount of structure in these profiles. And remember, I said a kind of fundamental argument of the classical model is that these 2 quantities are in lockstep. And clearly that profile isn't exactly the same as this profile. So there's kind of a question there. And so what we want to do is, can we use unsupervised machine learning techniques to try and identify different classes of mixing events that are actually happening in the near shore, rather than follow the traditional, this is the way you get a paper published in JPO, this is the way you analyze your data, right? So that's what we then tried to do. And the things I particularly have been talking about, this dissipation rate, chi, the destruction of buoyancy variance, and the buoyancy frequency, let's focus on those measurements and try and construct an appropriate data set. So what we do is we look at all these different profiles of epsilon and chi, here are the profiles, and then cut them up with the moving window into 50-meter blocks of data, or 50 meters of epsilon, 50 meters of chi, 50 meters of n squared, cut them all up, and then create a large data matrix of all of these different values of epsilon, chi, and n squared. And from now on, I want you to think of those as points in 3D space, right? The epsilon's the x coordinate, the chi is the y coordinate, the n squared is the z coordinate. And we want to see if in that 3D space, we're able to identify different generic classes of mixing events. And so what we do is we use a particular clustering algorithm called optics to do this. So I'll try and explain to you how optics works. So what you want to do is you want to think of a way. Here's like just a 2D representation. Suppose you have a data set that's got two characteristics, characteristic 1, characteristic 2. We want to be able to identify clusters of data which are all very close together and all share the same properties of these characteristics. So how are you going to do that? Well, you firstly say you want to think about what's a decent sized crowd, what's a decent cluster, right? And that's going to be min points. So you choose a number and you test robustness and write, supplementary materials of the yin yang. So you choose your min points. And then you need to identify a particular measure called a reachability distance, which is the maximum of 3 different distances. So the reachability distance of point xi in this space compared to point xj is the maximum of 3 different distances. One is an easy one, the Euclidean distance. Just you have a point here and a point there. How far apart are they? But these core distances are measures of how much the data in the neighborhood of that point is clustered. So you start off with a point, and then you draw spheres of bigger and bigger radius around that point until that sphere includes min points, which we chose to be 1,000. So if the radius is small, it means there's lots and lots of points clustered. If the radius is large, they're all spread out. So the core distance for that red blob is very small. The core distance for the yellow group is quite large. And then you line all your data set up with this reachability difference, x1 compared to x2. You just choose them randomly and line them up. And then you can identify groups of data. So the red group has a very low reachability distance. The yellow one is all spread out, so it's more spread out. The purple one is quite cramped. So you can then organically do this, and a picture will emerge if you actually have clustered data. And this is what we did to our data. And this is we being Miles Couchman, the great postdoc. And we found 5 clusters of data. The hot colors were associated with relatively high values of the buoyancy frequency, yellow, orange, and red. And the cooler colors, purple and blue, were associated with relatively low stratification. Now, I'm plotting, just for those with not great eyesight, I've written large chi, but it's actually the log 10 of chi. So there's a huge variability in chi here. And this is the log 10 of epsilon. So these are 2-dimensional projections of these 3-dimensional sets. And you see the way the data breaks up. You see the hot colors you see are associated with high n squared and are ordered by epsilon, because this is the log 10 epsilon in this direction. The purple and blue have very different values of epsilon, but a tiny value of chi, exactly the same value of chi, and basically low n squared. So we have managed to find 2 broad classes of mixing events that are separated further into subclasses, 3 of one and 2 of the other. But we by no means used all the data we had. We just clustered on epsilon, chi, and n squared, because we can then see other properties of this data emerge. So if we then look at the shear, the background shear as the vertical coordinate here, chi being this coordinate and epsilon that coordinate, you'll see the hot data lie on a perfect sort of line in this 3-dimensional space. As you go to higher shear, you go to higher epsilon and you go to higher chi. But the purple and the blue do not show this example. The chi is the same. They're correlated between high shear means high dissipation, but it doesn't mean anything about the mixing. But we also know where we took this data. And so we can start to understand the physics of what's going on by now going back to color the red data where we measured it, or where it was measured, relative to the distance offshore, the distance down, and relative to the background stratification. And you'll see now the red data is associated with being very near to the region of high density gradient, but near shore, that's its peak in terms of offshore distance. The yellow data is much further offshore, but is in exactly the same depth, and the orange is intermediate. And the blue and the purple are completely separable in their location. Blue is in the mixed layer near shore, and purple is deep offshore. And remember, they have virtually exactly the same dissipation rate, but we have managed by sorting, we have identified how they're clustered and we've identified the deep mixing events distinctly from the upper mixed layer mixing events, distinctly from mixing events in the thermocline where the density gradient is large. We've simply managed to identify them separately. But there's other data we have involved as well, which I haven't mentioned yet, which this data was collected on 2 different days when at the different stages in the tidal cycle, so the currents were different. And so then it emerged that we were actually seeing the blue data was associated with day 2 when the flow was west at upper levels. So the flow was westward, rubbing up against the reef, which was driving that mixing event. Whereas the purple event at depth and offshore was associated with the first day when we had a flow in the opposite direction across the reef. So it wasn't triggering the upper layer mixed event, but you had this strong shear at depth. So you had a deep shear instability was triggering the day 2 purple mixing event. And we were able to, we didn't search on looking for shear, it just emerged naturally in this particular way. And once again, I'm talking about day 2 was associated with westward flow. Remember, the red stuff was near the reef, and it was going this way near the reef. And so that was dominant as well for the deeper water as well, that it was strongly going across the reef. So we've managed to identify different characteristics mixing events, purely physics agnostically, reanalyzing our data. Now, can this inform our mixing modeling? And I'll remind you that I said that the classical model suppose there is a nice relationship between chi and epsilon. But actually, that transpired not to be the case once we reanalyze these data. So there's a bit of explanation that needs to go on with these plots, but I think they're instructive. So on each of these vertical profiles, remember this is log 10 epsilon, but it's just there so that you can see it. The dashed line is the mean value of this particular profile. And this is associated with the orange data, the sort of intermediately strong mixing events. And the shaded regions are the regions which are contributing 80% of the total amount in the profile. So epsilon is large here, because remember it's a logarithm, large there, but there's a lot of shading saying that there are several places where the dissipation rate is high. But if you now look at the places where the mixing is occurring, they're very rare mixing events. There's this little strip here and little strip there is doing 80% of the mixing associated with this entire profile. So if you then think about, okay, look at all our data and work out the fraction of the point, the first 5%, the first 10%, and so on, and how much they're contributing to the total, you'll see that there is very, very little difference. The solid lines are epsilon. Very, very little difference between the partitioning of all the different kinds of mixing events. Roughly speaking, if about 20% of the data gives you 75% of the contribution. But there is a great spread for the chi. You'll see that, for example, the red, the most vigorous mixing events, you'll see that 80% of the mixing is coming from only about 7% of the data. So rare events contribute overwhelmingly more significantly to the mixing. And so that then starts to give us a hint about the difference between the two insights, saying, look, gamma goes all over the place, but if you say gamma's 0.2, it fits much of the data. Because if you now actually look at what gamma does for the different data sets, this is ordered for the data on the amount of flux, the amount of mixing that's going on. And this is the value of gamma, log 10 gamma, centered on, and that's 0.2, the dashed line. So a lot of the data, and here it is, once again, the fraction of the data ordered by the weaker mixing events to the higher mixing events in this sense, showing the fraction of the data with this particular value. The dots are the mean. The dashed line is the 25 to 75% percentile. So if you're above it, you've got a very skewed data. And you'll see an awful lot of the data has gamma 0.2. And for all the different mixing events, that's the case. But virtually all the mixing is associated with extreme events that have very much larger gamma. You see, here's the data. All the mixing is happening for values of large gamma. here is this 25 to 75 percentiles. This is saying this is a very skewed distribution. So if you sample this data, you will often see a mixing event that's got gamma as 0.2, but it won't be doing much. You have to be lucky and careful in your analysis to identify the very efficient ones, but they're not just weird. They are efficient, and they are by far the largest contributors to the actual mixing that's happening. And this process has emerged by us being physics agnostic in the way we analyze the data. We just said, let's try and identify these different clumps and then look at the ones that are doing the most mixing. They're very, very efficient, very skewed distribution. And is it kind of associated with a kind of very optimal Kelvin-Helmholtz overturning with strong secondary instabilities? That's a possibility of what's actually happening. Okay, but I've mentioned this emerges, and so we start to say, well, we want to know if we can find the rare events. And so then this starts to make us want to think for the last 10 minutes or so about if we want to find rare events, that's a question about sampling. If it's a question about sampling, how many samples do we need to take to find rare events? Lots. And so we really should be trying to understand the probability distribution function of the mixing events rather than say we sampled something and that's the truth. Because this is something that I did with John Taylor and Paul Linden. We looked at a numerical simulation, a box of fluids, turbulent fluid, and we imagined that we then were observationalists and we dropped profiles through that data and measured the things the observationalists measured. We used the Osborne approach, worked out what the dissipation rate, worked out what the buoyancy frequency was, put in gamma as 0.2. We did the Osborne-Cox one, worked out what chi was, put in the n squared, and used that as our estimate of kappa. We did the very bad idea of just using the buoyancy flux, which has a reversible component. And we also used something called the thought scale. We looked at the overturning scales, and we used that in another parameterization, which is shown over here in the different colors. We've got the green, we've got the blue, we've got the purple, and we've got the red. And what we did with 3 different simulations, we looked at what the average, the actual value we wanted for kappa within the box of fluid, which is shown as the dashed line, and then worked out the statistical predictions of 1 profile, 5 profiles, 10 profiles, up to 20 profiles. And you'll see that probably the Osborne-Cox is the best. The blue one is closest typically to the actual dash line, but there's a great amount of uncertainty, and it's really taking a heck of a long time to converge to the right answer. And this is then saying this is not a good idea to do, because when you're an observationalist, it's very expensive to take lots of measurements. And so you don't want to keep taking lots of measurements. You want to use the measurements you've got to give you statistical information of the distribution you're actually sampling from. And that idea is what we then decided to do. We decided to use neural networks on a numerical simulation of the kind of sort of thing I'm showing here to do that sort of profile. And that's because there's another dirty secret in what's done in these stratified flows. Actually, they don't measure the dissipation rate. What you actually just measure is 2 components of the dissipation rate, the gradient tensor, the vertical gradients of horizontal velocity, and then you suppose the fluid is completely is isotropic and homogeneous, stationary, homogeneous isotropic turbulence, and then you suppose that you can then say, if I know 2 of the components of this tensor, I can just multiply it up. That's clearly not the case. This is a stratified simulation. You see this profound anisotropy. So now we can say, right, can we measure what we actually measure, but use neural networks to get an estimate for what the actual underlying structures are? And so that's what we did here, we being Sam Lewin, my PhD student. We took a large numerical simulation, 8,000 by 8,000 by 4,000, and we dropped profiles through it. And we measured what oceanographers measure on those profiles. We measured S squared, i.e. the horizontal shear components. We measured the density gradient. And then we compared, and then we said, okay, and then we knew what the dissipation rate at all points in those profiles are. And then we said, okay, imagine that what we've actually done is sampled from a distribution, a normal distribution, which has a given mean and a given standard deviation. and we've sampled and observed this epsilon. How can we go from the measurements to give us what we want, the statistical properties, the mean of that of that distribution of dissipation rate and the standard deviation of that dissipation rate? And what's nice about this kind of approach is that it allows us to be non-local. Because if we're actually looking at a set of data like this, and we're trying to work out what the associated standard deviation and mean of the dissipation rate that we're measuring here, and measuring here, and measuring here, and we're doing a convolutional neural network, we can have non-local information that will tell us the measurement, the thing we're working out here will know, in a sense, what the properties were up here. So it allows us to get both uncertainty estimates, but also beautifully, it allows us to reflect the anisotropy that is clearly inherent in this stratification. So we do that. And so that's what we're saying. We do this probabilistic neural network. We're basically trying to find this function that is taking the measurement of the shear and the measurement of the background density gradient to give us the mean and the standard deviation of the most likely distribution. We're sampling the epsilon that we're observing at that point. And we do this over and over again with 10,000 lines. And then we go to another set of lines and we do this process. And we sample from this from these distributions that we've calculated with means and standard deviations 10,000 times. And then we construct an estimate of what actually is of what we think the dissipation rate profile should look like. The picture here is constructed from our neural networks. The picture here is the truth. This is the log of the dissipation rate. Here, again, is the DNS, is the profile of this line turned round. That's the dashed line, and the neural network is the red line. And because we've done this sampling, we also know the uncertainty estimates, which is the shading. And so then if we think, which I think is really good, but what's even more amazing, I think, is what we can then say about the properties of these distributions. Because really what we want to know is what is the probability density function of dissipation associated with stratified turbulence at these particular instants. And of course, we know what the DNS, the numerical value is. That's the black line. Assuming it is isotropic, the classic surrogate model, that's the magenta line. Here for 1, 2, 3, 4, 5 different time slots. And our neural network is shown in a fetching shade of light blue. And you really, it's not just because it's a bad choice of color, it really is exactly the same as the black line. And particularly, the tails of the surrogate model are awful for the dissipation rate compared to the comparison. There's the neural network, and there is actually the truth that we have from our numerical simulation. So what by our approach of our analysis has allowed us to do is allowed us to say what we're measuring is we're not actually measuring the truth. What we're doing is we're sampling from an unknown distribution of this uncertain quantity, the dissipation rate or the mixing, and get insight into what the properties of that statistical distribution is. And that's the way you want to think about something. You're not, turbulence isn't really deterministic. It's about the properties of the statistical distributions from which you are sampling dissipation rate. Because oceanographers measure very, very infrequently, very few things. And so we want to give them tools to be able to use those measurements most efficiently to get a best estimate of the actual underlying distribution. So that's it. It's really important to understand turbulent mixing. It's really hard using physics arguments or to say anything generic. It is clear extreme events matter. And since extreme events matter, you want to use more sophisticated data-driven methods. If you start off physics agnostic and just identify things, use the algorithm to identify things you should think about, you can gain real physical insight into those different classes. But also, I'm trying to convince you that it's really useful to think also in this statistical fashion. That really what turbulent, when you're looking at turbulence, you're sampling from a distribution. This goes back to first class in turbulence, always talking about ensemble averages. That's what you really want to think about. Your measurement is a sampling from which you want to then think of a way to construct the ensemble average to have the proper insight. And it's something that becomes increasingly important when you do larger and larger simulations. The data, some of the data here was from simulations with 270 billion grid points. We're now up over 3.5 trillion grid points, but we haven't analyzed it yet. And you can't really think of normal ways to analyze that. You need to have some automated way to analyze it. So before I finish, I would just, of course, like to acknowledge the people who did all the work. I showed many of Chris Howland's pretty videos, and also videos of Ali Mashek, and I said John Taylor was involved. And of course, I always owe a great debt to Paul Linden, my PhD supervisor, and Dick Peltier, my postdoctoral supervisor. But here are the two brilliant young men who did the two projects. The case one, the Palau, reanalyzing the San Diego group's data. A Canadian, Miles Couchman, and that paper's in Press and GRL, great postdoc working with me. And Sam Lewin did the second thing, the probabilistic neural network, reanalyzing data from Steve de Bruynkopf and Gavin Portwood, and that is in Press for the NeurIPS machine learning conference. So thank you very much for your attention.